narcotic analgesics. These are the drugs that have CNS effects. We'll be looking at CNS stimulants. We'll be looking at anti-Parkinsonism drugs. We'll be looking at muscle relaxers. So we are really not able to do any practicals for this semester. So although we have been given a practical time, we will use it more often than not to also have lectures so that we can be able to finish on time. As you answer your questions again, remember, read the question properly. Read the question properly. And as you answer the question, ask yourself, what does the lecturer, what does the examiner want? So that you do not, sorry, allow me to reduce the volume, sorry about that. Ask yourself, what does the examiner want? So that you avoid writing a lot and very little. You write a lot and there is very little of the answer in whatever you write. Again, remember, whether you are using structures which have been given to you in the question paper, if you transfer that structure, if it's a simple structure, remember to number. I am insisting, remember to number your structure. Number it according to the way we've done it in class. But again, if the worst comes to the worst, and you cannot number it that way, at least it would be important to indicate a number. Because when you tell me there's a methox group at position 6, I cannot see your position 6. You are on the structure. I will not know where you are, which position you are talking about. So learn to number the structures appropriately. Learn to confine yourself to the question that you've been asked. Some of us just cram and they see a certain terminology, stereochemistry. They don't see the word stereochemistry. I don't know how they see structure-activity relationship. So instead of answering the question for stereochemistry, they go on a wild goose chase and they are talking about structure-activity relationship. At position this is a methoxy group. At position this is a hydroxyl group. And they give you the correct things, but they are not talking about the stereochemistry. So they waste all their time. When they are getting out of the exam room, they are very happy, convinced they have answered each and every question and answered it very well, but they read the questions wrongly. But I have seen a lot of improvement, and I'm still encouraging you as we have gone along. Yes, the unit may be challenging, but it is not impossible. Or it requires a lot of practice. Learn the simple structures substituents that we have learned, the methoxy groups, the amino groups, acetoxy. Those are simple groups that we have discussed through and through. There are also the heterocyclic rings, which have been very familiar to us, piperazine ring, the furan, pyrazole, such rings, the very, very simple rings again, piperazine ring. Those rings don't mention that one. Learn the names of those rings, pyroridine ring, and so on. The simple ones, as you learned in heterocyclic chemistry, they still remain. But I can't say I am happy. I've seen a lot of improvement, and I want to believe that this semester will even be better, that I will not even have any failure. Some students are really pushing me to really be very lenient on their papers because they give you very scanty information. Don't be left with the information. Don't put what is unnecessary. Again, don't withhold what is necessary. Number your structures well and answer the question, not with what you have crammed, but apply what you have crammed if you have crammed, or apply what I have taught you to answer the question appropriately. But as I have said, I am happy we are doing well. So the unit this semester, it is, I don't know why they, okay, I think we have changed. We are no longer calling it narcotic analgesics. There's a time they were calling it narcotic analgesics, but we are calling it now PHA 2513, pharmaceutical chemistry, CNS2 drugs. Why we are calling them CNS2, there's CNS1, where you study and conversants and so on. So in this unit, you study drugs like the narcotic analgesics. The narcotic analgesics are also the opioids, general anesthetics, centrally acting muscle relaxants, anti-Parkinsonian drugs, CNS stimulants, and hallucinogens. And when you look at these drugs, that's why we are saying it was almost not possible to be able to do practicals on them. Most of them are controlled drugs. Like if you look at, of course, narcotic analgesics, the general anesthetics, you cannot bring them to the lab. So we might not be able to do practicals, as I have said, for this unit. And for each of this class of compounds, because of course, again, when you look at them, kindly note, they are disconnected. They do not have really any connection, apart from that most of them work in the central nervous system. They will not have any structural, apart from those who, of course, in the same group will have structural resemblance. And some of them will not. Like the general anesthetics, you see it's drugs that have completely different structures but have similar mode of action. So the narcotic analgesics, the general anesthetics that we have seen. So for each class of compounds, we will discuss the same things we've been discussing before. We will look at the general structural features, the classification of the members, the prototype. Sometimes where possible, we look at synthesis, structure activity relationship, which we have always done, mode of action. I do not do a lot of pharmacokinetics because I know that you do a lot of pharmacokinetics in pharmacology, because considering all these drugs, all these different classes of drugs, then we have to be careful, otherwise we will not finish. But we do look at metabolism, which is very important, metabolism, elimination, and the stability and some of the assay methods. So that will be our unit this semester, and I welcome you for us to walk the journey together. Again, if there are any issues, any questions, kindly you can put them on the message on the public chat, or if you have any challenge somewhere, you also are welcome to contact me and call me. I do not have a problem. Now you are seniors. You are actually seniors, and very soon you'll be meeting out there where you are doctors, and there is no issue of who graduated or qualified before the other. So I want you to participate. Let it be an interactive process where all of us, when I ask you a question, kindly try and answer the question. Attend classes, as you know, for Pharm Chem. Now you know it. It is important to attend classes. So yes, starting with the narcotic analgesics and just an introduction. We can note that opioid analgesics reduce the perception of pain without loss of consciousness. So these are analgesics. They do not have any other characteristic like anti-inflammatory, antipyretic, as we have discussed before with the non-steroid or anti-inflammatory. These ones basically is just reduction of pain. The natural opioids are derived from the opium, which is a partially dried latex harvested from the opium poppy, Papaver somniferum. It's important for us to note that the initial lead compound, that is morphine, is naturally produced. But as we have always discussed, it's naturally produced. It has very good analgesic activity. It might have some challenges, and therefore, again, need for structural modification to get semi-synthetic products which have better activity and, of course, lesser toxicity. Opium contains morphine. It also contains codeine. It contains noscapine, papaverine, and thebaine. But we will concentrate mainly on morphine and codeine, and we'll be able to see what's the difference between morphine and codeine. Are there differences in their structures? Do the structural differences bring about activity differences? We'll be able to know that. I believe you have heard of codeine. Codeine, I think now it's controlled, but it used to be a component of very many cough mixtures, but it also does have abuse potential. So I think now it's a bit more controlled. The Bane is a convalescent drug that produces no analgesia, and as such, it is not used clinically. So that's why I've said we will not bother with the Bane. It is an important synthetic intermediate in the production of some synthetic opioids because of its natural source. Morphine and morphine derivatives are referred to as opiates. As we have said, they are derived from the plant opium, from the dried latex harvested from the opium poppy, Papaver somniferum, and therefore the name opiates from the plant from which they are derived. The classification. When we look at the narcotic analgesics, we will classify them according to their activity, their mode of action. Are they agonists? Are they antagonists? Are they mixed agonists? Are they partial agonists? So that's the classification that we will do according to their receptor interaction, and so we can classify them according to their receptor interaction and even their source. Receptor interaction. With this receptor interaction, what I mean here, when they interact with the receptor, are they pure agonists? Are they pure antagonists? Are they partial agonists? Are they mixed agonist antagonist? So that's what we're talking about. So when we talk about, of course, their source is whether they are natural or semi-synthetic, because most of them are either natural or semi-synthetic. So natural, we have opium alkaloids, where we have morphine. Of course, some are natural. We do have some in the lab that are totally synthesized. Like when you talk about methadone, those drugs are synthesized in the lab. So we have those which are natural, where we have opium alkaloids like morphine, like codeine. We have those which are semi-synthetic analogs, whereby you start either with morphine, and you will see that you start with a very big complex structure and you break it down. You break it down. Unfortunately, I forgot to tell you to draw the structures as I usually tell you, but after this, make sure you can draw the structures. So you start with the complex structure of morphine and you break it down to various classes of drugs up to the time morphine is 5 rings. You break it down up to the time you only have only either one or only 1 ring or 2 rings, and the compound has good activity. So we'll be able to see which is a pharmacophore. We have discussed before. Are there areas within this morphine molecule which you must be maintained for analgesic activity? So we have the semi-synthetic analogs, we have the hydromorphone, we're going to look at the structure, we have the oxymorphone, we're going to look at the structure, another oxycodone. When we talk about the oxy, remember it shows introduction of an oxygen. When you talk about the hydro, is where you have removal of a hydroxyl group. Synthetic compounds, we have meperidine. Meperidine is also the pethidine. I hope you've heard of. I believe you're doing your ward route, so you must have come across these drugs. Meperidine is the same as pethidine, which is really used in maternity ward. We have levofanol. Again, all this methadone, as I had said, some fentanyl. This is a general anesthetic. Our fentanyl, lamifentanil, and levomethadil. All the remifentanil. Fentanyl, I believe you have come across it. A lot of it used in theater. Our fentanyl, all those being general anesthetics. And of course, for a general anesthetic, that drug must have a very rapid onset of action. So you can see we are starting from a drug like morphine, which is being given orally, and we are structurally modifying it, or because we are looking at narcotic analgesics. They are all, even the synthetic compounds, have a structural resemblance with morphine, and we are structurally modifying morphine to get drugs that have a very rapid onset of activity, and of course very effective, because remember, when you talk about general anesthetics, they are giving you a knockout. So very effective in pain, having a very rapid onset of activity, and of course also when, and also having a short duration also of activity, because when you go to theater and they are through with the operation, you'd want to have been given a drug whose effects wear out very quickly, and therefore these drugs must also have a very short duration of action. So now we have looked at the sources, and we have said you can have natural, you can have semi-synthetic, and you can have totally synthetic compounds. Then we looked now at the interaction with the receptor, and we can have, I should start with pure agonists. Did I leave one? Oh, goodness, why isn't it? Sorry. Yes, I thought I had also based on receptor, because I also should have started with pure agonists. Anyway, let's see what I have. I have not left anything here. I don't have. I think there's a slide I've left out, because I can see these are mixed agonist, antagonist. I think there is a slide I have left. So what we will do for that, for on receptor interaction, let us first leave that, because I can see I have a slide. I have mixed agonist, I have partial agonist, I've left two. I have a slide I have left. Okay, I have let me say narcotic. I have narcotic antagonists. I have mixed agonists. There are two I have left out, so I think I'll correct that. So that classification, we can always look at it later, because I think I have left one slide out by mistake. So that we will discuss. Then we can also classify this drug based on the chemical structure. Opium alkaloids are classified into two types. That is on the structure. We have the phenanthrene derivatives, and we look at the structure. When we talk about phenanthrene derivative, it is these three rings here. Let me put a pointer. So we are looking at the phenanthrene derivative. It's these three rings. Those three rings are the ones we are calling phenanthrene. And under phenanthrene derivatives, we have morphine, we have codeine, and we have thebaine. Of course, when we look at the actual structure, we will see that we will add two other rings, but the morphine, the codeine, the thebaine, their basic structure is the phenanthrene structure. And then we have the isoquinoline derivatives. And when we talk about, we have papaverine, noscapine, and asin. These are the ones we are saying we are not going to look at them. The ones we are going to look at them is the phenanthrene derivative, but you can't see the structure here. Benzyl isoquinoline. This is this structure here. Benzyl, benzyl, and isoquinoline derivative. So that we have papaverine, we have noscapine, and we have nasin. But as I have said, we will only be discussing the phenanthrene derivatives. So we will discuss the morphine, the codeine, and of course the morphine derivatives. Codeine is a morphine derivative, and amongst many others. So we will not go to the isoquinoline derivatives. Then I think, though this might look like, I think this has come a bit too early, and I want us to first look at the structures of the structure of morphine before we look at the morphine rule. So let us first understand the basic structure of morphine. And the first thing I want us to understand is the numbering of the morphine. And before you even look at the numbering, let us look at the type of rings we have. You can see ring A is an aromatic ring. Ring A is an aromatic ring. Ring B is a cyclohexene. You can see this is a double bond there. Cyclohexene ring. Ring C is also a cyclohexene ring. You can see double bond at position 7, 8. And then you have ring D. This should be ring E. Sorry, and this should be ring E. They have interchanged that. So this, the ring D, which is this one there, you can see 4, 5, 6. So it's a 6-membered ring. It's a 6-membered ring, and then it has a nitrogen. So I believe from what we have studied before, you can understand that's a piperidine ring. That is a piperidine ring. So you have a cyclohexene ring, ring D, piperidine ring, and a ring E, a dihydrofuran ring. So those are the 5 rings that make up the morphine. It's not moving now. So those are the 5 rings that make the morphine molecule. Then from that, of course, we are saying, and I have done the correction, that is ring A, that is ring B, that is ring C, this is ring D, and that is ring E. Then from there is now the numbering. For morphine, of course, we are starting at that position, number 1, number 2. Number 3 for morphine, a very important substituent, a hydroxyl group. As we have discussed before, we'll be able to see what is the relevance of that hydroxyl group. And then from number 3, of course, you come to number 4, you do not number that position there. Number 5. So number 5 is now on ring C. Number 5, and again at number 6, For morphine, you have a hydroxyl group, but we'll be able to see you can't change these groups. Even this group, you can change it. That group, you can change it. But once you change it, we will see whether there is any change in activity. And of course, our double bond position 7, 8. And then after position 7, 8, the next group, the next number goes to ring B. And you can see it's position number 9 here. And then now you go to ring B, 10, you come back, 11, 12, 13. If you look at number 13 carefully, you can see number 13 is a unique chiral center, which is a chiral center which is quaternary. It's a quaternary chiral center because you can see all the substituents that are coming from that chiral center are alkyl groups. They are alkyl groups and therefore quaternary center. And we will always see that that is an important feature of the narcotic analgesics. And then from number 13, you go to number 14. Another important substituent is this one. We will see that that substituent can be changed and it can be replaced with a hydroxyl group, and we'll be able to see what are the effects of changing that hydrogen. And then, of course, 14, and then from now, number 14, we move on to the piperidine ring. So we go to the piperidine ring, and we have this position 16. So I believe this is position 17 there, 15, 58. This and they have numbered. It's also funny. So we should have this as our position 15, 16 and 17. So because you see this was already position 9, so that's position 14, and then we jump to this one, which unfortunately, although they have called it 16, should be 15. This is position 16, and this is position number 17. Now this position 17 again, remember this is our piperidine ring E. So when we look at it, we have already numbered that. We can't number it again. Numbered that one, numbered that one. So we go 15, 16, and 17. Very, very important in all the narcotic analgesics or the narcotic analgesics. It is important to note this position number. It will not be position number 17 in all the structures, but it is important to note that in all the narcotic analgesics, you will have a tertiary amino group for maximum activity. A tertiary amino group for maximum activity. And it might not be position 17, as I've said, because we will dissect this structure and bring it down until it's a very simple structure which has, as I said, 1 or 2 rings only. So now, after you have understood that, sorry about that mistake in numbering, and we will look and find out whether we have something better. So after you have understood that, now we can look at the morphine rule, because you have understood the structural features of morphine. And the morphine rule, it can be obeyed, but sometimes there can be exceptions. But the exceptions are very, very few. The following structural features are found in most opioid analgesic analogs and are collectively referred to as the morphine rule. Occasionally, there are some exceptions to this rule, just occasionally. And as we move along, we will be able to identify the exceptions. A tertiary nitrogen, as I have already said, tertiary nitrogen with a small alkyl substituent. This small alkyl substituent can occasionally be the exception, whereby you can have larger substituents with retention of activity, sometimes with change from agonist to antagonist. Like sometimes their compounds, we'll find they have a phenyl ethyl, phenyl ethyl substituent at that position. Phenyl ethyl is a large substituent, but the compound with the phenyl ethyl substituents have also been found to have activity, and that's why we have said there are few exceptions, but in most of the compounds, they have a small alkyl group. It must be a tertiary nitrogen. I did mention, and I showed you position number 13, a quaternary carbon. Remember, quaternary carbon means that carbon is a chiral center, a carbon that is substituted with 4 alkyl substituents. there is no hydrogen. And again, when we look at all the compounds that we call the opioids, whether morphine or morphine analogs, we will identify a quaternary carbon atom. So again, very important. A phenyl group or is isosteric. Remember, we have discussed isosterics of phenyl group, like the thiophene. We have mentioned the thiophene can be an isosteric, but you find for actually almost all the compounds that have got good analgesic activity, they do have a phenyl group. So even when we break this to the simplest compound where we have methadone, we will still identify a phenyl group within the structure. So all its isosteric equivalent directly attached to the quaternary. So this is very important. Directly attached to the quaternary carbon. Then you have a 2-carbon spacer between the quaternary carbon and the tertiary nitrogen. I think that is the only one we haven't seen. I didn't show you that. Why this is taking so much time to move. Moving very slowly. So if you look at the one we were looking at before, let me clean it up. So we are saying 2 carbon atoms. So remember, this is our number 13 here, is our quaternary carbon. There, you don't have to cram that it's number 13. In some of the structures, it will not have the number 13. What is important is that we are looking at that quaternary carbon and we are looking at this tertiary nitrogen. Remember, the tertiary nitrogen is part of the ring. So it's part of the pyridine ring. And you can see that is carbon 1 there and carbon 2 there. So carbon 15 and carbon 16 are between the quaternary carbon, carbon 13, and the nitrogen 17. And that is something you note, that you do have a 2-carbon spacer between the quaternary carbon and the tertiary nitrogen. Again, sometimes you can have a bit, again, of an exception, but that is what is observed in most of the narcotic analgesics and the opioids, morphine and the analogs. And even if you have exceptions, the exceptions are very few. So with that now, we can now be able to look at some of the structures. I'm sorry, I should have told you to draw the structures. And you can see this is now what you're calling morphine. We've already looked at that. You can see at position number 3, it has a hydroxyl group. At position number 6, it has a hydroxyl group. Now, when you come to codeine, the only difference between codeine and morphine is that for codeine, at position number 3, it has a methoxy group. That is the only difference. And that difference, as we are going to see, changes the activity of this compound, and we'll be able to see that it is more of an antitussive. That is why you get it in cough mixtures. Then from there, I believe we have had the compound heroin. If you look at all the other positions, the structure is the same. I believe you have had the compound, the name heroin, and heroin is diacetyl morphine. If you look at this here, that's an acetyl group there. This is an acetyl group there. And what these acetyl groups do is that they increase lipid solubility. That compound moves rapidly in and you attain very high concentrations. And that is why heroin is one of the highly abused drugs, because of its lipid solubility, it is able to move very fast into the brain, attain high concentrations, and have a very good effect. But we will notice that this group there, even when that drug gets into the brain, has to be hydrolyzed for that drug to have activity. Then you have the other class. If you look at now the next compound, this one we call it morphinan. And you can see the difference between the morphinan and the morphine. You have this and there. The and is usually a hydroxyl group in the morphinan group. You can see the position, this position is still the same. And that position will still be position 17 because you have only removed the furan ring. You have only removed the dihydrofuran ring, nothing else. And you know we did not give a number to this. So the numbering will remain the same. Again, you see the influence. Again, there was a double bond there. You have removed your double bond. So those are the two changes that you have in the morphinan compared to the morphine, whereby you have saturated ring number C, and you have removed the dihydrofuran ring. Then you have the hydromorphone. Again, whenever you have the morphone instead of morphine, morphone means that at position number 6, in place of the hydroxyl group, you have a carbonyl group at position number 6, and the hydro means there is saturation there. You have added hydrogen there, and there is saturation at that position. Again, we'll be able to see how those effects, how those changes, the molecule is the same, we will be able to see how those changes affect the activity. That removal or saturation at that position, you have added hydrogens, and of course also oxidation of the hydroxyl group to a carbonyl group or to a ketone. Again, hydrocodone. As I said again, when you see codone, it means that the hydroxyl group at position number 6 is that group has been oxidized to a carbonyl group, and of course it is a hydrocodone. Codone from codeine means that position number 3, in place of the hydroxyl group, you have methoxy group, so that it changes first of all from morphine to codeine, and then from codeine you do oxidation of position number 6 to codone, and then you do saturation of position 7, 8 to hydrocodone. And then you have the oxycodone, and when this oxy means another addition of an oxygen, and that usually is at position number 14. If you look at your structure, this is in position number 14, this is position number 13, where we talked about the quaternary carbon. So oxycodone, any of the compounds you see an oxy, it is because they have an extra oxygen at position number 14. They have an extra oxygen in form of a hydroxyl group at position number 14. So that is an oxycodone, and you can see everything else is maintained. Then we have another compound we call levofano. Now, if you look at levofano now, you can see that we have come from, we have again, we have 1, 2, 3, 4. So we have removed. So levofano is an example still of it's an example of a morphinan, because in levofano you can see the structure is the same. The N 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. The only difference is, what is it? This compound and this compound are the same. Yeah, there is a slight, yeah. So morphinan, sorry, yeah, it's correct. Morphinan is the general structure. These compounds are called morphinans. And then now levofano is a specific example of a morphinan. So all of them, we call them morphinans. But now when you put the actual group at R, and you have put it as a hydroxyl group, then that compound is levofano. So you can see again, levofano has the same structure of morphinan, whereby there is saturation of ring C. And let us also note, in the morphinans, there is also removal of the hydroxyl group at position number 6. Saturation, removal of the hydroxyl group at position number 6, and also, of course, removal of ring E. We will be able to see how does that change the activity of these compounds. Of course, that is not the end of the compounds. We also will be able to look at the benzomorphans. We will also be able to look at phenol. There are many. There are about 5 categories of derivatives of morphine that we'll be able to look at and study the differences in their activity because of the structural modification. So those were just some of the examples. So I hope we are together up to there, looking at this structure, trying to break it to understand the numbering. We have looked at the numbering. We have also looked at the structure, and by looking at the structure of morphine, codeine, and also looking at the structure of the morphinan like levofano, we are saying you do not require. We already have said you can remove ring E and do other structural modification, remove the hydroxyl group, saturate the molecule, at position 7, 8, and the compound still has activity. So we are saying the whole structure, the whole morphine structure is really not necessary for activity. But of course, when it is morphine, it has to have all those groups. But you can remove some of those groups, remove a whole ring, and the compound even has better activity. So we look at the morphine structure requirements. The following structural features are important for morphine's pharmacological profile. We have already said a rigid, because now we are looking at morphine. So please understand. The following structural features are important for morphine, not for morphine analog, for morphine itself. If you are talking about morphine, for it to have activity, it requires a rigid pentacyclic structure consisting of, we have already said, a benzene ring, two partially unsaturated cyclohexane. This should be cyclohexene. Make sure that this is an E. Rings B and C, a piperidine ring D, and a tetrahydrofuran E. So you require, it should be a dihydrofuran, not tetra, dihydrofuran ring. Yeah, dihydrofuran ring. So we are saying we require those rings if we are talking about morphine. Ring A, B, and C are the phenanthrene ring system. This ring system has little conformation of flexibility. You can see these rings are annulated. They are joined to each other, so they are rigid. They are rigid. They do not have any flexibility, conformation of flexibility. They are just flat and needed for activity. You do have the 2-hydroxyfunctional group. You have the carbon 3 phenolic hydroxyl group. They're calling it phenolic because it is joined to an aromatic ring. And any hydroxyl group joined to an aromatic ring is a phenolic hydroxyl group. And then we have an alcoholic hydroxyl group at position number 6, because ring B, this ring, I think it's in fact ring C. Ring C, this ring is not aromatic. It is just a cyclic ring. It is a hydrocarbon cyclic ring, not aromatic, and therefore the hydroxyl group is alcoholic. Again, we will look at the derivatives. This is for morphine, but we want to look at the derivatives and see, do you require the hydroxyl group? And as you have seen, we can say with certainty already, the hydroxyl group is not needed for activity in the derivatives, because the morphinans do not have a 6-hydroxyl group and have better activity than morphine. So we can be able to say that. And either linkage between carbon 4 and carbon 5, and we have seen that, and saturation between carbon 7 and carbon 8, a basic tertiary amine function at position number 17. So these are the structural requirements for morphine itself. And then if you look at morphine, we can be able to identify, even before we look at that, we should be able to identify the chiral centers. Should be able to identify the chiral centers. Of course, all the centers within the aromatic ring do not have any chirality because of aromaticity. So you move from position 4, you come to position 5. And of course, you can see that is our first chiral center there. Remember, chiral center is that center that has 5 different substituents. So here the only omission is a hydrogen, and you can see that substituent, that substituent, that substituent are all different. So we can identify that as our first chiral center. Position number 6 again for morphine, where you again have a hydroxyl group. Again, position number 6 is a chiral center. Those are 2. Whenever you have a double bond, for sure there is no chirality whenever you have a unsaturation. So again, that is position number 7. We are trying to see, we have gone 5, 6. Then we can go to position number 9. We look at position number 9 again, chirality there. Again, you have 4 different substituents at position number 9. Now we have 3 chiral centers, and then from there we move to position number 13, which we have even said not only is it a chiral center, it is a quaternary carbon. It's a quaternary carbon where all the 4 substituents are alkyl substituents, and then finally we go to position number 14. So you really do not need to cram. You can be able to identify the chiral centers from the morphine. We'll find out position number 9 is the chirality of position number 9 is very important in the activity of the these drugs of morphine. So it has 5 centers of chirality, as we have seen, and I wanted us to identify them ourselves: carbon 5, carbon 6, carbon 9, 13, and 14. Morphine exhibits a high degree of stereoselectivity of analgesic action. So at the receptors, we require, there is a lot of stereoselectivity for analgesic activity, and it's the liver totally morphine which has activity. See the liver totally morphine amphoteric, and if it is amphoteric, can we be able to explain, is it ionized at physiological pH? And if it is ionized, can we be able to explain? And if you look at the morphine, morphine, we can say it has 2 groups. It has one group which is highly basic. If you look at the tertiary amine, one, it's a tertiary amine. It's joined to an alkyl group. The alkyl groups are electron donors. So that nitrogen is not it's not attached to an aromatic ring. So that nitrogen, knowing it has a lone pair of electrons, that nitrogen is highly basic, which means that nitrogen can be protonated at physiological pH. It is a base, it accepts proton. But at the same time, morphine at position number 3, it has a phenolic hydroxyl group. And you know, phenolic hydroxyl groups also exhibit very, very weak acidic properties, and therefore, overall, morphine will be basic in nature. So we can't say it contains more than acidic, phenolic, and a basic tertiary amine functional group. The amine group is significantly more basic than the phenoacidic group morphine, as well as a majority of narcotic analgesics are functionally basic compounds, and I have explained why that, and we have seen it's a tertiary amine. The alkyl groups will push the electrons, and therefore the nitrogen has a lone pair of electrons, so it is protonable at physiological pH, and that means most of the morphine compounds, or most of the morphine formulations, for you to be able to increase their water solubility in the formulations, you can give them as acidic salts, whereby you add a bit of acid and the hydrogen and the nitrogen is protonated. Morphine exists as a cation at physiological pH and readily forms salts with appropriate acids such as hydrochloric acid and sulfuric acid, and normally the commercial products are either sulfate or hydrochloride. Remember, we deliver these drugs when they are in their non-ionized form, like when they call it the base form, you find that they have very low water solubility. Always remember, when you give a drug, first it must go into the solution so that it forms an equilibrium of the non-ionized and the ionized. The non-ionized is the one which will penetrate the membranes. So that drug must have some appreciable water solubility. So to improve on the solubility of these drugs, because you look at the structure of morphine, it is highly hydrocarbon, highly hydrophobic, and therefore very low water solubility. So you derivatize it in the acidic salt, improve the water solubility, and then when it gets into the stomach, or when it gets into the place of absorption, it can go into solution. Once it goes into solution, it can equilibrate, and therefore the non-ionized is the one which penetrates the membrane, and as the non-ionized penetrates, more ionization, more solution, dissolution occurs, and until the drug is completely absorbed. Even if, of course, the drug is given as an injectable, the same will happen. We've already looked at, I think, ring numbering, so I don't think there is anything new. We have seen morphinan. If you look at the morphinans, like levofano is where we said it does not have the funan ring, so sometimes they are called 4,5 alpha epoxy morphinans. The morphinan refers to rings A, B, C, and D of morphine, hence epoxy morphinans. Morphinans, more specifically 4,5 alpha epoxy morphinans. So when it comes to this, means we can't be able to call morphine 4,5 alpha epoxy morphinans. Ring B and D of morphine is termed. So these are the things we have done. So the B and D of morphine is termed morphan. Then A is aromatic, that's flat. Ring C is in the boat conformation due to a double bond. Ring D is a nitrogen containing piperidine ring. Then E is the ether or epoxide. So these are things that we mentioned. We have 5 chiral centers. So we can have very many stereoisomers 2 to the power 5, but indeed the one which has been found to have activity is the levoisomer, or the levomorphine is naturally produced, the absolute configuration. This is important. So those chiral centers have this absolute configuration. When we talk about the absolute configuration, we are saying the specific configuration of each carbon atom. So the position 5 has the R. Fortunately, they keep alternating. So once you know the 5 is R, you'll be able to remember all of them. So as long as you remember, the first one is an R, the second one, which is 6, is an S, the next one, which is 9, is an R, and you can see we have it has been highlighted with a different color because that position very important, as I already said, 13S and 14R. So that is the absolute configuration. The configuration at carbon 9 is the most important, which determines the orientation and distance between the proton and nitrogen and the phenyl ring. In most cases, the more active isomer is rotatory. Usually the isomers with an S configuration are dextrorotatory. So we are saying this stereochemistry is very important at position number 9. It determines the distance between the terminal nitrogen and the phenyl ring. When we look at the receptors of morphine, we will see that the terminal nitrogen and the phenyl ring interact with the receptor. There are some of the sites that interact with the receptor, so they require to be placed in a very special way. So, of course, when you change stereochemistry, when you change the configuration of certain carbon, then you change the spatial arrangement of that molecule. When you change the spatial arrangement, that means you could change it such, like when you change 9R to 9S, you change such that the nitrogen and the phenyl group do not maintain the optimum distance that is required for interaction with the receptor. So remember, how stereochemistry interferes with binding is because of giving you the optimal distance, the optimal size, the optimal shape of the molecule that is required to interact with the receptor. So it is important for us to note that even for most of the drugs, when you talk about the dextroisomer, more often than not, it is because the position number 9 has changed its stereochemistry from R, to S, giving a molecule, though very similar in structure with even the morphine, that molecule has differences in its stereo arrangement, and because of that difference, then it cannot interact with the receptor. So this is just to show us what we talked about, the acid and base. So we are saying if you put the morphine in very strong base like sodium hydroxide, then it can give you that. You put it in very strong base, it can act as an acid, and therefore the hydrogen will be extracted. The morphine will be acting as an acid only at the phenolic hydroxyl group, because phenolic hydroxyl groups, as you see, they are very, very weak acids. If you react it with not very, even when you react it with a bit of weak acids, then you find, as we have said, the nitrogen at position number 17 will be protonated. And indeed, that nitrogen is even protonated at physiological pH. And therefore, once it's protonated at physiological pH, it also helps in the solubility of that drug within the aqueous media of the blood and good distribution. Next, I want us to look at the metabolism. And this structure is metabolized in very simple ways, very, very simple ways. Perhaps even before we look at that, we can look at the structure. So again, we have morphine there, and we know there are various accepted groups. Like whenever we see this group there, that is a nitrogen attached to a methyl group, we already know that you can have oxidative and dealkylation. We have this group here, the hydroxyl group. We know again you can undergo methylation. That group there, you can undergo methylation so that you can get a methoxy group. And that position. Again, this group here can undergo also glucuronidation, such that you can get that position. You can get a glucuronide molecule at that position and also at that position. And they're actually very, very simple methods of metabolism. So we are looking at that one, and you can form is conjugates the position number 6. You can also get the morphine 3, again the glucuronic molecule conjugates with the hydroxyl group at position number 3. You can get what we said, codeine, and with codeine it is methylation of the hydroxyl group at position methylation at the hydroxyl group at position number 3 to give us codeine. You can also get, as we have said, oxidative end dealkylation. This is not right. For it to be correct, you must have a hydrogen. When you leave it as a line, it shows that it is a methyl. It tells us it's a methyl group. So you can have oxidative end dealkylation, and of course with oxidative end dealkylation, you will get no morphine, and you'd expect that compound to have slightly lower activity, because we did say a tertiary amino group is necessary for maximum activity. So with that, we can then look at this morphine biodisposition and metabolism, limited oral bioavailability to extensive fast-pass metabolism. So it has limited oral bioavailability. And we have, of course, you know what fast-pass metabolism is. It is lipophilic. It has a very large portion which is hydrocarbon, but less so than other opiates such as heroin. And we did mention heroin because of, you see, morphine has a hydroxyl group there, and that those two free hydroxyl groups, the hydroxyl group bring in more water solubility than the methoxy group. So once you block the two hydroxyl group, the resultant group compound, which is heroin, has very high lipid solubility. And as I said, that is what makes it to be absorbed very fast and to move into the brain and to bring a lot of toxicity. So metabolism, you can, as we have said, you can have 3 and 6 or glucuronides, oxidative end dealkylation, or methylation to codeine, which is a minor pathway elimination primarily in urine as a glucuronide. Remember, the minute you put a glucuronic acid, when you conjugate any of those groups, the glucuronic acid, you remember glucuronic acid has a carboxylic acid, has very many hydroxyl groups, increases the water solubility drastically, and therefore increases the elimination of that compound. Now, the next is for us to understand just a mention of the types of opioid receptors. There are different types of opioid receptors. Don't know whether you have done these compounds in pharmacology. I will not really go into much details, but you have the mu, you have the kappa, and you have the gamma receptors. So the mu receptors are responsible for the supraspinal analgesia mediated. In other words, these ones are mainly agonist receptors. So the mu receptors are mainly agonist receptors. They are responsible for respiratory depression, gastric motility. Reduction is mediated by mu2 subtypes. Mu receptor produces euphoria, physical dependence, and meiosis. So they also produce analgesia, but they can also produce these other side effects: euphoria, physical dependence, and meiosis. The kappa receptor appears to mediate spinal analgesia through, so you can see all of them are mediating analgesia. So they are responsible for analgesic activity through the kappa subtypes and supraspinal analgesia through kappa 3 type. Produces respiratory depression, dysphoria, hallucinations, meiosis, sedation, and cotinic effects. But what we are saying, they also bring about analgesic activity. The only problem, and this is a major problem of these narcotic analgesics, one, of course, as we have said, they can cause dependence. They can cause dependence, and another very major problem with them is that they can cause respiratory depression. And most of the people who will die because of overdose, they will die because of respiratory depression. You can see whether they bind the mu or the kappa, they will produce respiratory depression, and that can be also quite a problem. Then you have the gamma receptors. Activation of gamma receptor produces against spinal analgesia, respiratory depression, affective behavior, enforcing actions, and reduced GIT motility. So all these receptors, so any of these receptors, mu, kappa, and gamma, can be stimulated by any of the drugs to bring about analgesia. But at the same time, these receptors can be blocked. When you talk about an antagonist, always remember, antagonists do not trigger any pharmacological activity. What they do...
Hello, Daktari.
Yes.
Hello.
Yes.
The third one, is it gamma or delta? The number 3.
Oh, yeah, it's delta. Yeah, sorry. Thank you. Yeah, it's delta. And antagonists do not elicit or do not trigger any pharmacological activity. What they do is they sit on the receptor, like what we call the dog in the manger. A dog sitting in the manger, and it will not eat what is not meat. So it does not trigger any pharmacological activity. It sits on that receptor and prevents the agonist from sitting. So it will have structural features that will allow it to sit on that receptor more tightly and bind for a slightly longer time, prevent the agonist from binding. So the next was mechanism of action. And all we are saying is that, of course, when you get the opioid analgesic, it will go for the mu receptor, it will bind the delta receptor, it will bind the kappa receptor. And since you have seen all these receptors have agonist activity, it will trigger a series of processes or chemical processes whereby in triggering those processes, it will cause a blockade. It will block pain transmission. And some of those ways we can say it can cause is through inhibition of activation of voltage gated calcium channels, and therefore block neurotransmitter release. It can also increase potassium conductance outside the cell to cause hyperpolarization of the cell, thus again reducing its excitability. It can also bring about inhibition of adenyl cyclase. Adenyl cyclase is the enzyme that cleaves or that causes cleavage of ATP to give you AMP plus the 2-phosphate. So you can have inhibition of adenyl cyclase, and you can see adenyl cyclase gives us cyclic AMP, and which brings about phosphorylation of ion channels and increases channels of channel opening. So once you inhibit adenyl cyclase, there will be a decrease in the channel opening. Once there is a decrease in the channel opening, then there will be a decrease in conductance. Once there is a decrease in conductance, then there will be a decrease in the pain transmission. So those are 3 of the ways in which these drugs will act. They will go for the mu receptors. Remember, these receptors are within our bodies. The mu receptor, the kappa receptor, the delta receptors are all within the body. So this is just the same as we have said. Act on the G protein coupled receptors. They inhibit adenyl cyclase. They will promote potassium channels and inhibit opening of calcium channels. They will reduce neuroexcitability and increase potassium conductance. Remember, we have said if you increase potassium conductance outside the cell, you will bring about hyperpolarization and again decrease the pain transmission, cause hyperpolarization, and shows inhibitory pathway and reduce pain. So these drugs actually are inhibiting, they're acting as inhibitors of the neurotransmission, and in so doing, they are reducing the pain. Now, we can move to the SAR, and I hope this one now I've numbered it correctly. So again, when we look at the structure-activity relationship, the first thing we must start with is to understand the numbering 1, 2, 3, 4, 5, 6, 7, 8. And again, from 8, we move to ring B, 9, 10, and then we go back to ring A, 11, 12, and our carbon there, which is our quaternary carbon, and then 14. And then from 14, we jump to 15, 16, 17. So what you need to remember always, you must number this structure such that your nitrogen carries number 17 And of course, that you must remember this carbon, which is very important. This is our 9R carbon, and you can see it has an alpha-oriented hydrogen so that it maintains that kind of chirality. So that is the numbering. Again, of course, when you look at this structure of importance, we're looking at morphine first. Of importance is to understand the important groups, that hydroxyl group, that amino group. Those are very, very important groups. And of course, they have a lot of role, especially in binding our receptors, as we will discuss as we continue discussing the compounds. So again, when we talk about structure-activity relationship, one of the structure activity relationship features that has been mentioned is stereochemistry. So stereochemistry is part of structure activity relationship, but structure activity relationship is not part of stereochemistry. So stereochemistry is a constituent of structure activity relationship. So when we are talking SAR, we need always to remember that stereochemistry is very important. This we have already mentioned. Morphine has 5 chiral centra. Only the laboratory isomer is active, which has 5R, 6S, 9R, 13S, and 14R configuration or absolute configuration for activity. It exists as a, in fact, that's the next sentence. It exists as a single natural occurring laboratory isomer, and we have already discussed that. It can undergo epimerization, carbon 14, but not beneficial to analgesic activity. So that can happen, but that does not really change analgesic activity. And that now is what we have already mentioned. We have already discussed this. This is just showing the chiral centers of morphine, chiral centers. And by now, I do believe we do understand chirality. Any group that has 4 different substituents and does not have a double bond. The hydroxyl, so now we're looking at the SAR of morphine, the hydroxyl group in the phenolic ring. The basic nitrogen is needed for activity and seen in all potent mu agonists. So that hydroxyl group there and that terminal nitrogen is indeed necessary for the activity of morphine. And even when we look at most of the other drugs, you will see, of course, again, there could be one exception or so, but you will see that most of the drugs that have got good activity do have the hydroxyl group and the terminal terminal. Not only is it terminal, but usually terminal tertiary nitrogen for maximum activity. Activity can be preserved or enhanced by removing other rings. And we're going to see, like when you remove this ring here, you increase activity. So the morphinans have higher activity than morphine. Why? This oxygen here, this, if you look at it, we can call, because it's a ring, that's why we say it's a dihydro, not tetra. If it's tetra, then it would be having 4 hydrogens out, but it has only 2 hydrogens. So dihydrofuran ring here. Look at this oxygen of the dihydrofuran ring. It is only increasing. What hope I'm not lost again. Whole rings and still retain activity. So activity can be preserved or enhanced by removing other rings, changing the hydroxyl group to just hydrogen, or to methoxy group, lowers activity as seen with codeine. So we are saying that group here, 3 hydroxyl group, if you change it to a methoxy group, you will lower activity, but you also coincidentally introduce new activity, and codeine has antitussive activity. Even when you change that group to a hydrogen, again you lower activity, because this group here is important in interaction with the receptor through hydrogen bonds. The nitrogen is mostly tertiary with a methyl substitution in morphine. The size of the substituent nitrogen dictates potency and agonist or antagonist. Again, we will mention that the size of the substituent here can dictate the kind of activity you have. Like you have compounds like naloxone, naltrexone. You will see that the groups that are at that position are slightly larger. slightly larger. So slightly increasing that group slightly up to up maximum of 5 carbon atoms, still can give 3 to 5 carbon atoms, you can give us activity. When you increase beyond, again, it can give us activity, but we'll see most of those compounds acquire antagonistic activity. When again you increase beyond 5, again you recoup the agonist activity. Again, we will look at that and give the necessary examples. Reduction of position 7-8 double bond also increases activity, but we will see this double bond, the reduction, in other words, you will saturate, it normally goes hand in hand with oxidation of position number 6. Like, what we talked, oxidation of that position to give us the own, morphone, codone. So once you saturate that position, and at the same time you also oxidize position number 6, then the resultant molecules have even much, much higher activity. Inclusion, so this is just a summary. Inclusion of a hydroxyl group at position 14 again increases activity. That gives us the oxy derivatives again with increased activity. Removal of hydroxyl group at position number 6 increases activity, and if even oxidation to the carbonyl group, like in the codones, in the morphones, also increases activity. Oxidation of hydroxyl group to keto group, add carbon 6. So the first one was complete removal, like where we talked about the morphinans. They do not have that group there, and they still have good activity, but they retain the hydroxyl group at position number 3. So these are summary. Again, we'll go back to it and look at them one by one. Oxidation of the hydroxyl group to ketone group at carbon 6 increases activity. There is also reduction of the 7-8 double bond, e.g. the hydrocodone. So that's why I say the position 7-8 usually goes together with the position number 6 oxidation, so that there is appreciable. There is still increase in activity, but it's more appreciable. It's slightly more significant when you do reduction of position 7-8 and oxidation of position number 6. Acetylation of hydroxyl group number 6 increases activity, like in 6-methyl morphine, 6-methyl morphine, where you do 6-acetyl morphine, where you have acetylated that group there, you find that it has high activity. When you acetylate that group to give you the dimorphine, or what we call heroin or diacetylmorphine, then the compound even becomes more active. So removal of the ethyl linkage produces compounds called the morphinans that have even much higher activity, and I've explained that oxygen only decreases lipid solubility and does not seem to have any effect or any binding on it doesn't seem to have any interaction with the receptor, and therefore its removal improves on the lipid solubility, the penetration of that drug, its ability to penetrate the BBB, get into the brain, and also bind the necessary receptors. So when you look at this is just a summary. So you have that phenolic hydroxyl group. That is what we are calling the ether bridge. It's just to tell us which is which. That's a alcoholic hydroxyl group. Alicyclic unsaturated linkage, tertiary nitrogen. Of course, that is our aromatic ring. And we will look, as we have said, that whatever I've given you was just a summary. And we will look at each structural modification in detail so that we can understand the same. So let us start now with peripheral modification, ring A analog. So we're looking at the peripheral modification. The peripheral groups are like this group there. That's a peripheral group. The groups that are found on the outside. We start with the peripheral modification of peripherally modified morphines, and we are calling them ring A analogs. And we are saying ring A and its 3-hydroxyl group is an important structural feature for analgesic activity. I'm just now going one by one so that we further understand. We had already talked about the general ones. So removal of the 3-hydroxyl group reduces analgesic activity, esterification of the carbon 3-hydroxyl group, and once you do a esterification of morphine, you get codeine reduces narcotic analgesic activity, the larger the ether group, the lower the analgesic activity. So when you do a esterification, you lower the activity, and indeed the resultant compound requires. So in other words, we are saying we require free 3-hydroxyl group for optimal activity, analgesic. You need to mention analgesic activity for this compound. However, compounds such as codeine possess very useful antitussive activity. So that is the hydroxyl group at position 3. It is necessary for activity. So we are even saying if like you remove that group and you get the 3-deoxymorphine, you can see the relative potency is 0.1 minimum. When you compare morphine and the 3-deoxymorphine, relative potency is 0.1. So you can see indeed that 3-hydroxyl group is very, very important for activity. And as we will see later, it is of course because it is thought to interact with the receptor through hydrogen bonds. Then you have the morphine, that's our morphine. You can see codeine, relative potency 0.15 in terms of analgesic activity, but it has that additional good activity whereby it has antitussive activity, and then you have the ethyl morphine, relative potency 0.1. So you can see now this that is the ethyl, that is the codeine, that is the ethyl morphine, 0 point relative activity 0.1. So you can see it has gone down a little bit. This was 0.15, this 0.1. Again, we have said the larger that group is, the lower the antitussive activity. Then this is another group, big group put at that position to give us 4 codeine, and again further reducing the activity. So this one is just to show us that that group, we are saying the 3-hydroxyl group is important for activity. Then we can say something about codeine. Why? Because you will, well, even as you go around, when you go for your ward rounds, codeine is a very common drug. So it's important to know something about it. It is available again as a salt, the sulfate and phosphate salts. Again, remember, because of the tertiary amino group, you can react this the codeine with sulfuric acid, all phosphoric acid to get the sulfate and the phosphate salt. As a free base, can also be available as a free base. It can be available as tablets, as elixir, or solution for injection. In your pharmaceutics, of course, you do formulations, so you do understand all those formulations. The 3-methoxy group protects the 3 position from glucuronidation as occurs with morphine. So, of course, it will not undergo very fast. It will not undergo very fast fast-pass metabolism because of that protection. But we have said because of the 3-methoxy group, the compound has lower activity. It is used as an analgesic and antitussive. Of course, we are saying it is more safer, and that's why you can get it in over the sometime back. It used to be in the over-the-counter cough medications, but I think there is a law which was passed and most of those drugs were removed, mainly because also the codeine also on metabolism will also be changed to morphine, so it can still have a bit of, not very much, but it can still have some morphine-like activity. It is metabolized by cytochrome mediated oxidative or dealkylation, you see, to morphine, cytochrome mediated oxidative N dealkylation again to nord-codeine, conjugation to the 6-O-glucuronide. Again, the same methods we had talked about. It's only that now, of course, it has a methoxy group at position number 3 that has to be removed, and then, of course, the other methods, metabolic processes are the same. The derivatization of the carbon 3-hydroxyl group by esterification increases and analgesic activity minimally. So again, we are saying this carbon 3-hydroxyl group, but this is esterification. It is not esterification. The esterification reasons being esters are highly unstable. So the minute it gets into the body and brain, it can very rapidly be hydrolyzed by esterases to release the free hydroxyl group. But the minute you put the ester group, the advantage of the ester group, which is quickly hydrolyzed, also blocks the hydroxyl group and therefore increases the lipid solubility of that molecule. So when you do esterification of that position, of course, it will just increase a little bit because of the increased lipid solubility. Esterification or acetylation of both. Now I've gone to both. So here I'm on both 3 and 6. This is what gives us heroin, and that yields heroin, a compound which is both more lipophilic and more potent. And it is more the potency of heroin is mainly because of the increased lipid solubility and the ability for that molecule to penetrate the BBB very quickly, attain very high concentrations in the brain, and then the fact that the ester linkage of the 3-hydroxy group is very labile, and therefore it will be very easily hydrolyzed and released for you back the morphine. The 6-hydroxy group does not require to be hydrolyzed. The drug will still have activity even when the 6-hydroxy group is acetylated. But for the 3-hydroxy group, hydrolysis must occur. But since we have attained very high concentration, the ester group ester linkage is very weak. You have high levels of esterases in the brain. Heroin has much higher activity than morphine. So the primary factor involved in increased analgesic potency is increased lipid solubility and high distribution to the CNS. Heroin is metabolized primarily by hydrolysis of the carbon-3 O-acetyl moiety to the 6-monoacetyl morphine. The 6-monoacetyl morphine may be further hydrolyzed to morphine, which is conjugated. Again, the metabolism now will be the same. So we are saying the first step is that the 3-hydroxy group will be hydrolyzed, and the fact that this drug is penetrating the membrane very rapidly, it will attain very high concentrations, and that is what these addicts want, that rush, that the effect of the heroin is very, very fast compared to the effect of morphine because of the very high concentration that is attained. And that I think that finishes the A ring. I've also brought in the C ring a bit, and I brought it in because it was important for us to compare morphine and heroin, or morphine and the 3-acetyl, the acetyl morphine. It was important for us to understand the difference in activity, or what brings the difference in activity between heroin, or what we call dimorphine or diacetyl morphine, and morphine itself. Then now we look at ring C. The 6-hydroxyl group of morphine is not required for analgesic activity. We have said that. Look at the morphinans, is not there. Look at even the heroin. It has been blocked. So you do not require a free 6-hydroxyl group for activity. Elimination of the 6-hydroxyl group actually enhances activity. So when you remove it, there is increase in activity. Esterification, it said when you remove it, the molecule is even able to bind more appropriately. Esterification of this group with relatively small alkyl groups also increases activity. Esterification means, as we have said, when you esterify it, you do not require to hydrolyze it. It can work even when it's esterified. That is why esterification of 6-hydroxyl group will increase activity slightly compared to esterification of the 3-hydroxyl group. Remember, the 3-hydroxyl group, you require the free hydroxyl group, whereas we have said you do not require the 6-hydroxyl group. So when you esterify the alcoholic 6-hydroxyl group, you increase lipid solubility, and therefore the molecule will be able to bring better activity. Small alkyl groups also increase activity. Esterification of the 6-hydroxyl group, and we have mentioned that increases activity as in the main hydrolysis metabolites of heroin, the 6-monoacetyl, the 6 monoacetyl morphine. 6-monoacetyl morphine also increases analgesic activity. This increased activity appears to result largely from the enhanced, again, lipophilicity of these compounds and the increased ability to penetrate the CNS. So we do remember we are saying we do not require the 6-hydroxyl group. So both the methoxy, of course, and the acetyl derivatives will have activity. Again, they will have a better penetration of the BBB, not any change in the binding of the receptor. But there can be slight change when you remove, but not when you acetylate and when you you verify. But mainly is because of the increased lipid solubility, where the molecule can have better penetration of the BBB. So you have the morphine there, you have the 6-deoxymorphine, and you can see we are seeing relative potency compared to morphine. It has increased with 10 just by virtue, by removing the hydroxy group. You have increased the lipid solubility. And as I said, also you increased, when you remove the hydroxy group, it is said that you do improve on the binding of that molecule to the receptor. Then the 6-methoxymorphine, again, there is a slight increase, relative potency of 5. E6-ethoxymorphine, again, there's a slight increase of 2.5. Of course, when you have large groups, always remember there is steric hydrans, and steric hydrans does influence the binding to the receptor. And then, of course, you have the 6-monoacetylmorphine, and you can see again there is an increase, relative increase of 4.2. So all we are saying is you don't, of course, need to remember the relative potency. We're only saying just to show that when you structure modify the 6-hydroxyl group, you will have an influence on the activity of this compound. I think we have also looked at this. That is the morphine. That's the 3-acetylmorphine. The acetyl group, of course, we say it increases the lipid solubility a bit, so there is a slight increase in activity. But the diacetyl, you can see the diacetylmorphine has much more activity because of the lipid solubility. Yes, you drink C. Remember, ring C has a 7-8 double bond. So 7-8 double bond of morphine is not required again for analgesic activity. Oxidation of the 6-hydroxyl group of the dihydromorphine to yield hydromorphone further increases activity. Once you saturate position number 7-8, you get now the hydro derivative. When now you oxidize, as I said earlier, the 6th position, you get the one. Remember, the one stands for ketone. So now it is hydromorphone because you have also added hydrogen. You have saturated or you have actually reduced. So it's a reduction of position 7-8 and oxidation of position number 6. Substitution of a 14 hydroxyl group, again the 14 group again is in ring C, further increases, and that of that is now hydromorphone. So remember, the hydromorphone does not have a double bond at position 7-8, is a carbonyl group, and now further you add a 14 hydroxyl group a structure as in oxymorphone. So anytime, as we had already mentioned, with the oxymorphone produces a further increase in analgesic activity, and you can see the increase is quite big. Oxidation of the 6-hydroxyl group of morphine directly as in morphone without reduction of the 7-8 double bond does not significantly alter the analgesic activity. So you're saying oxidation of the 6-hydroxyl group directly as in morphone without reduction of the double bond does not significantly alter analgesic activity. So the two require to go hand in hand. You do reduction of position number 7-8, you do oxidation of position number 6 to get the hydromorphones or hydromorphone derivatives, and that further increases activity. Again, examples, you have that is morphine, you have that is your dihydromorphine, you can see that, and it's just 1.2, and then you can see the hydromorphone, whereby there is oxidation and removal. You can see appreciable increase in activity, and then you can see the oxymorphone further increasing the activity. This methyl group should be up here. Further increase in activity, and you can see if you just remove the if you just do oxidation, in fact the removal of the double bond, removing that is having a better influence than just when you when you just oxidize. So this is just mere oxidation. You can see the relative potency is just 0.66. There is basically no improvement of activity. Metabolism, again, of hydromorphone should also follow almost the same. So the hydromorphone, remember when talk about hydromorphone, again, that is oxidized, that is a double bond there, and you can get the hydromorphine. get the dihydromorphine, whereby this again undergoes reduction to give a 6-alpha, the 6-alpha and the beta. So you can get both alpha and beta products. You can get both alpha and beta products. And then you can also get glucuronidation of the hydromorphone, whereby you still have that hydroxyl group. Definitely, you can also get the oxidative end dealkylation, but we are looking at the most common routes of metabolism. Then, thought we looked at codeine. Have I gone back? SAR of codeine. So we have mentioned reduction of the 7-8 double bond activity. I think it's now the codeine itself. So we have we want to do the same thing we have done to morphine, whereby you can see reduction again of the 7-8 double bond, as in dihydrocodeine increases activity relative to codeine. Oxidation again also will increase the activity. 14-hydroxy substitution produces a further increase in analgesic activity. So we are saying the structural modifications you do to morphine, you can also do to codeine, and they will still give you activity. So you can see that is what we are calling this is a dihydrocodeine, has slightly higher activity than codeine. You can see the dihydrocodeine is removal of the double bond. The hydrocodone, where you have removed the double bond, and you have that again further increase in activity. Just the same thing we have done. And then when you put the 14-hydroxyl group, so that you get the oxycodone, again, there is further increase in activity. So all we are saying is that you can do the same structural changes, and you will get a similar improved activity. This is relative, the 0.3 relative to morphine, remember, and this is 1.15, 5, and 7 relative to codeine. So you can see all of them, even when you change, apart from the oxycodone, the other two products of codeine, even when you do structure modification, they still have lower activity than morphine. It's only the oxycodone which is actually relative potency is 1, so it's actually having similar activity to morphine. But for when you compare the analgesic activity of the derivatives to that of codeine, you, just as we saw with the structure modification of morphine, there is a increase. There is a increase in activity when you do those structural modification. Formulation and metabolism of oxycodone. So we are therefore saying oxycodone will have much, much more analgesic activity. And remember also, the more the analgesic activity, unfortunately, the more the toxicity. Because remember, these drugs, you did see when they increase analgesic activity, it is through binding those receptors, the mu receptor, the kappa receptor, the delta receptor. And when they bind, they also bring the toxic effects, the euphoria, the dependence, and so on. And therefore, the tolerance, the dependence. So therefore, as you increase the analgesic activity of these compounds, kindly do remember you will also increase their toxicity. So oxycodone for sure will have more toxicity to cause euphoria. It will cause respiratory, in case you give very high doses, it could also cause respiratory depression. So again, given as the hydrochloride salt in tablets and capsules, it has an analgesic, also an antitussive activity, because remember it's a derivative of codeine, but we have also seen that relative to morphine, it has much, much higher activity than the hydrocodeine or codeine itself. Primary metabolite formed from oxycodone is the 3-conjugate glucuronide. Hydrocodone, again, it is available as by tartrate, salt in tablets and syrup. It has analgesic and antitussive activity. Again, it's just understanding these compounds metabolized by oxidative dealkylation to hydromorphone, oxidative end dealkylation to norcodeine, reduction of the 6-keto group, the 2 epimeric hydrocodones, the way we saw that you could the 6 keto group can undergo can undergo reduction to give you either the alpha or beta hydroxyl group. And that's what we're calling reduction of the 6 keto group, the 2 epimeric hydrocodals, because they are alcohols, 6 beta hydrocodal and 6 alpha hydrocodal. We are calling them hydro because already there is a reduction or saturation of position 7,8. The epimeric 6 alcohols can undergo oxidative O dealkylation again to give you the morphos. The morphos now, the epimeric 6 alcohols can undergo oxidative O dealkylation to use the epimeric hydromorphos. That means you've removed the methoxy group at position, the methyl group at position number 3, so that you return to the morphine. Morphos means it's a morphine. So you can be, it is simple. You are just removing subsequent groups. And once you remove the methyl group at position number 3, it becomes a morphine. But we are calling it a morpho because it does not have the double bond at position 7. It has now acquired a hydroxyl group at position number. It has acquired a hydroxyl group at position number 6. So this is just the reaction. Each of the 6 hydroxyl metabolites have pharmacological activity equal to or greater than the parent compound. 6 alpha hydrocodal has much lower, which is 1/6 of the as potent. So these are just the details of the products. But all we are therefore saying, what is most important for us to learn is that you can do structural modification. You can do structural modification of codeine, just as you can do structural modification of morphine. And of course, the metabolism of the compound is structure dependent. Metabolism of the compound is structure dependent, and the route of metabolism for sure would depend on what group do you have at position number 3, what group do you have at position number 6, what group do you have at position number 17. So we are saying that for the codeines, when you have when you saturate the double bond at position number 7,8 and you have a ketone at position number 6, it can undergo epimeric, what we have said, reduction to the alcohols. And then, of course, after that, it can also undergo oxidative O demethylation at position number 3. So the codons can be changed into the morphos. So this is just dependent on the structure. And once you understand the structure and you understand the various types of metabolic processes, oxidative N dealkylation, oxidative O demethylation, reduction, and so on, oxidation from alcohol to ketone, then you can be able to understand the metabolism of this compound. Oxycodone is available again as a hydrochloride salt, tablets and capsules. It has an analgesic again, an antacid activity. Remember, it will have oxycodone, we have said, again, just remind ourselves that it has equivalent analgesic activity to morphine because of the fact, especially because of the addition of the 14 hydroxyl group, reduction and also oxidation of the ketone, but of the alcohol at position number 6. But the reason mainly, what really increases the activity is the 14 hydroxyl group to make it an oxide derivative. Primarily, I think we have seen that. I hope I have not gone behind. Then we move on to modification on the alicyclic ring. Of course, this alicyclic ring, I think this one we have mentioned in tier 2. So I don't need to go back there. So again, this is now, I hope it makes more sense. I've just brought back the same compounds so that now you can understand the naming. That is morphine, that is codeine. Now you can understand much more because of the methoxy group there. That is heroin or 3,6-diacetyl morphine or dimorphine. And you can see we have discussed it, acetyl group there. We have not got the morphinans, we got to them later. This is the hydromorphone. Now you can understand why hydro saturation there, why morphone, there is a ketone there. Now you should be able to understand hydrocodone, again, on that there, hydro, again, that saturation there, oxy, meaning the oxy, because of this hydroxyl group there. So now that we have discussed them, I hope you can understand better. It's a codone. It's only a codone, remember, when there is saturation there, because if there is, so there is saturation there, and also there is oxidation at that position. So it's important for us to understand that. So it's a codone, and of course, for it to be an oxycodone, you must have that hydroxyl group at that position. So anytime you put that hydroxyl group at that position and you have a double bond, and that becomes an oxy of whatever you're looking at. Now, we have looked at the peripheral rings, because we have not looked at the piperidine ring, because that, I think, will be the final one. There's a lot of structural modification. So let us now, number 2, look at modification of on the phenyl ring. That the phenyl ring itself, and we did mention that you do require a phenyl ring or its isoster, but the phenyl ring is responsible for maximum activity. An aromatic phenyl ring is essential for activity. Modification of the phenolic hydroxyl group decreases activity. Any other substitution, the phenyl ring diminishes activity. So you do require that phenyl ring, and this will be evident in all the analogs and derivatives of morphine up to methadone that we will observe. We will see that all of them retain the phenyl ring. Indeed, we did even mention that that is part or requirement within the morphine rule for it to have activity. Modification of the tertiary nitrogen, which is up there. A tertiary amine is usually necessary for good opioid activity. Tertiary amine, the size of the nitrogen substitution can dictate the compound's potency and its agonist and its reverse antagonist property. In other words, the size, you require tertiary amine, yes, but the size of R can determine the activity. Is it a strong agonist? Is it an antagonist? And so on and so forth. And again, we'll be able to look at the various groups, and we'll be able to look, as I have said, we have naloxone, we have naltrexone, be able to look at them and see how that change in that group also affects the activity. The N-methyl substitution is so we are saying when you have the N-methyl substitution, it gives us good activity. When increased in size, when increase the size of the when you increase the size of the substitution to 3 to 5 carbon, it results in analgesic, in antagonistic activity. So up to 3, I think I made a slight mistake there. So up to 3 carbon atoms, we are safe. Up to 3 carbon atoms. When we increase beyond 3 to 5, I think that's the same thing I said, antagonistic activity. Beyond 5, we revert back to agonist activity. So antagonistic activity, like when you look at naltrexone, when you look at naloxone, you see one of them is a methyl cyclopropane methyl cyclopropyl group, whereas the other one is an allyl group. So once we increase beyond 3 and above, we increase 3 and above, we get antagonistic activity, and below 3, we get good agonistic activity. So that again is a very good rule. But I have said again, beyond 5, like in the ethyl phenyl derivatives, you find that they do have good agonist activity. Still larger, so that's the next, still larger substituents of nitrogen returns agonist property of opioids. For example, N-phenyl ethyl substitution is 10 times more potent than N-methyl group. So it's a bit strange, and it's not really, let me not say it is strange, because it is well explained that when you put large groups, the morphine, when you look at the receptor, the morphine has about 4 different sites on which it can bind. We start with D, C, B, and A. And you find that when you increase the size, like the ethyl phenyl group, it is able to interact with a site within the receptor, the site A. When you look at morphine, which does not have that, B group, it cannot interact with A. It will interact with D, it will interact with C, it will interact with B. But it doesn't have the interaction with A. So when you have drugs that have a large group at that position beyond 5, they are able to interact, of course, beyond 5, but to a maximum. They are able to interact with that site A, and the more the interaction with the receptors, for sure, the better activity. So it can be explained that the larger group there, like the phenyl ether substitute at that position, it is because it allows the resultant compound to have optimal interaction with the A site, which does not happen when you have small groups. When you have groups of 3 to 5, it is because it allows the resultant molecule again to interact with the receptors in an antagonistic manner. In other words, when it binds the receptor, it blocks the receptors, it does not trigger any agonistic activity, but interferes with the receptors and does not allow for agonists to bind. N-allele, that's what we have said, N-allele, and cycloalkyl groups lead to narcotic antagonistic property. So again, you'll be able to look at that and be able to understand it better. Epoxide bridge, we have mentioned this bridge, and this is the bridge between carbon 3 and carbon, I think, 4. And we have said when you that epoxide group, which gives us the dihydrofuran, removal of that bridge increases activity, increase in lipid solubility, better penetration of that molecule through the BBB bridge in morphine structure results in the compound that is referred to the morphinans. The morphinans are prepared synthetically as a synthetic procedure yielded compound is a racemic mixture. Only levoisomer possesses opioid activity, where the dextroisomer has useful antacid activity, for example, levofanol and butorphanol. So we are only saying that you can't be able to prepare these compounds synthetically, but it will give you the racemic mixture, whereby, remember, the racemic mixture means one is levo and the other one is dextro. And the dextroisomer, as I had said that earlier, dextroisomer is responsible for antitussive activity, but the levoisomer is the one that is responsible for analgesic, good analgesic activity. Even the dextroisomer will have analgesic activity, but it will be much lower than the levoisomer. So you'd require, the best product would be the levoisomer. Levofanol is more potent, is a more potent analgesic than morphine, because we are saying in levofanol, you have removed the ether linkage, increased lipid solubility, and resultant compound has much more activity. So now we can this is just, we have been looking at the structures. These are some of the compounds that we have. Of course, this is a general structure. That, of course, is our R. Yeah, this is our R prime and R prime prime. So when you look at morphine, of course, that's a hydrogen methyl, ethyl morphine. Here you have, there's a C2H5 and everything else. Codeine, we have looked at it. Heroin, we have looked at it. And naloxone. Look at naloxone. We're going to discuss naloxone. Unfortunately, we're not able to look at the classification. So naloxone, you can see it has an increased size here. So we expect it not to be fully agonist. It should also have some antagonist activity. Those are some of the structures, and it is important that you draw all the structures, that as many as you can find, for the narcotic analgesics. I'm only giving you a few examples. Dihydromorphine derivatives, again, we have looked at quite a number of them. The dihydromorphine, of course, if it's a morphine, it will have a hydroxyl group there. It will have a hydroxyl group there. It's dihydro because it does not have, it has saturation at that position. The dihydrocodeine will be the same. It will be a methyl group here, and the others will be the same. Then you have the hydromorphone derivatives. Again, remember, morphone means that we have discussed all this, that group there. So that we change, we you have the hydromophone. We expect, of course, that to be a hydroxyl group, and that R to be a methyl group, and of course R prime to be a hydrogen. Oxymophone, again, this is the oxy of this group there, to have a hydroxyl group at this position, and that is the R prime, to have the hydroxyl group there, and of course it will have a hydroxyl group here and a methyl group there. Hydrocodone, as long as it doesn't have an oxy, that will be a hydrogen. It is a hydro that is saturated, and a ketone at that position. Oxy, again, whenever you see an oxy, it means the position number 14 must have a hydroxy group. So that tells you. So when you have a hydro, it means it does not have a 14 hydroxy group. When it's an oxy, is when it has the 14 hydroxy group. But if you look at this, the position here for both the hydro and the oxy are the same, the difference being the presence or absence of a hydroxyl group at position number 14. So we have mentioned addition of a 14 beta hydroxyl group results in a dramatic increase in activity in the dihydromorphinone cells. So that hydroxyl group is that one there. So once you add that hydroxyl group, there is drastic increase in activity, and that must be that it is able to change the spatial arrangement of this molecule so that that molecule interacts better with the receptor. Any questions? Are you okay? We are done with modification of the nitrogen group, but I will go through it again, and I think in details, because there's some of the changes we did not mention. I mentioned in general. So the next is we look at the modification of the nitrogen group in details. But do we have any questions? At least we have done well. Can we look at the modification of the nitrogen group? Or are you saturated? We had already looked at it. It's just a summary. Fox group. I hadn't seen that question. Position 1, 2, 3 should be between 4 and 5. I just read what had been written. These people sometimes make mistake. 1, just to check. 2, 3 should be epoxy group between position 4 and position 5. Again, that's important. It's not 3 and 4. It's an epoxy group between position 4 and 5. Correct. So epoxy group between 4 and 5, removal of that epoxy group gives us the morphinans. And we have said the morphinans have much higher activity because of increased lipid solubility, because that's an oxygen. Oxygens increase hydrophilicity, and therefore removing of that group increases lipophilicity, and therefore the compound penetrates. Remember, penetrates the BBI, brain-blood barrier, gets into the brain, higher concentrations, and therefore gives you better activity. Thank you again for that correction. Can we finish with the nitrogen, because we had already looked at it? Are you saturated? Are you able to take a little bit more? Let me hear from you. Of the nitrogen substituent, and we have already mentioned, so this is actually revision. Methyl is the optimal substituent for agonist activity, and ethyl is passable. In saying it's passable, it will also work, but it does not have any advantage. So methyl can be termed as an optimal group. If the nitrogen substituent is a hydrogen, analgesic effect is reduced, and an addiction liability is lowered. We understand, we say the lower the analgesic activity, the lower, because for you to have low analgesic activity, it means the binding to the receptor is lower, and therefore even the side effects, euphoria, dependence, tolerance, all of them will go down. And of course, you will get the you get the no derivative. When you remove the methyl group and you place it in hydrogen, the resultant compounds are the no. Addition of a phenyl either substituted in place of methyl results in a 14-fold increase in activity of a morphine. Again, that we have discussed that, and I have explained, as we'll see even later, that because the ethyl phenyl derivative is able to bind an extra receptor which morphine does not bind, and that receptor is receptor A. Quaternary ammonium derivatives such as N,N-dimethylmorphine have no analgesic activity but do have other activities. So again, you cannot do dimethyl substitution of the morphine, you lose activity. If the nitrogen substituent is a bulky alkyl group such as propyl, fact, usually methyl propyl, isobutyl, or especially allyl and cyclo. So they had already put propyl alone. So propyl, isobutyl, or especially allyl and cyclopropyl methyl, the compound becomes a narcotic antagonist. So we already had mentioned between 3 and 5, especially for allyl, cyclopropyl methyl, those compounds become or have analgesic activity. Again, this is something we have done said. The R configuration alpha to the nitrogen, that is the carbon number 9. The R configuration alpha to the nitrogen. If you remember, the position number 9 is the one alpha to the carbon 9. I mean to the nitrogen, to position number 17 is optimal for mu receptor affinity. And this again we have said that that position number 9 is the one which determines whether it's dextro or levo. You require that position to have the R configuration. Removal of the N-methyl decreases lipid water partition coefficient or decreases the lipophilicity. It's the same thing. The removal of the N-methyl group decreases the lipid water partition coefficient, decreases the lipophilicity. Quaternization decreases again the lipid water partition coefficient, because if you put dimethyl group, you quaternize, you put a dimethyl group, or you quaternize, then it will be, the nitrogen will be positive. And once it is positive, quaternization means you're putting 4 substituents, it will be positive. Again, that will decrease lipid water partition coefficient tremendously. The N oxide also will decrease. If you add an oxygen, again, an oxygen will bring in lower lipid solubility, and all those factors, all these structural modification are resulting in decreased lipid solubility, decreased penetration of the BBB or lipid membranes, and therefore decreased activity. Increased size of the N-alkyl decreases increased size of the N-alkyl, especially where we have said the cyclopropyl methyl, the allyl, decreases mu receptor affinity through steric hydrons, but increases lipid water partition coefficient. As length of the N-alkyl increases, the mu receptor affinity decreases. So we have said when you increase up to 3 to 5, you now decrease the mu receptor affinity until the chain is about 5 carbons better better if it's an aryl alkyl. Then mu receptor affinity starts to increase slightly due to induced dipole interaction with allosteric A site. So that's what we have seen, it is a phenyl ring. So what we have, this is the same thing we have been talking about, that we are saying that once you increase, so we have said the length of N-alkyl increases, mu receptor affinity decreases. So between 3 and 5 carbon atoms, you decrease the affinity. Mostly, more often than not, you do have steric hydrances, and therefore you decrease the interaction. But now when you increase it further, as we have said with the ethyl phenyl, it is now not having, the influence here is that this new group has an interaction with a new site, or that site is always there, but the morphine is not able to interact with it. But when you increase the size to the ethyl phenyl derivative, then you have interaction through induced dipole interaction with the allosteric site A, and that is what makes compound which have a very huge group to have some activity. So you can see this is nalofine. As we said, nalofine has that activity, it has allyl group there. This is naltrexone, and you can see naltrexone has the cyclopropyl group there. And one of the things that has been added to naltrexone, as you can see, it's a pure antagonist. Again, we'll go back there because I say there was one slide which was missing. When you look at naltrexone, it also have, for purposes of increasing activity, better binding, you can see it has a hydroxyl group at position number 14, and it has also the saturation of 7-8 double bond, and also it has a ketone at position number 6. And you see that even that's not even naloxone also, which is also a pure agonist. This is not a pure antagonist. Naloxone, which is also a pure antagonist, naloxone has this allyl group up here in place of the methyl in place of the methyl cyclopropyl substituent. It has the allyl group there, but it has also these two. Those two groups improve on the binding of the antagonist to the receptor. But because of the increase of this group, as we have said, beyond 3 carbon, from 3 carbon atoms, that's 1, 2, 3, 4, 5, 1, 2, 3, 4. So it has 4 carbon atoms. Between 3 and 5, we say the binding is more antagonistic than agonistic. And especially when we look at, as I've said, of the pure antagonists, there are also these added groups which improve on that compound, binding the receptor more and bringing antagonistic activity. Then branching and saturation or strained ring structure in the N-alkyl substituent leads to antagonism. That's what we have said. Even if you bring branching and saturation is like the allyl group, the strained is like this cyclopropyl group, and if you do branching, or at the very least partial agonism. So if you change that group there, sometimes you can get partial agonist. By partial agonist means a partial agonist is that drug that even when it binds the receptor does not give you the full agonist activity that is required. It is not a full agonist, and therefore we are saying that can happen, as we have already pointed, when you change that group. And we have given examples. We have given naloxone. We have given naltrexone is a pure antagonist, and also naloxone. There's naltrexone and also naloxone. Those are pure antagonists. And of course, naloxone will have much lower agonist activity compared to morphine. So it leads to either antagonism or at the very least partial agonism as found in naloxone, and pure antagonism, as I have said, as found in naltrexone and in naloxone. Naltrexone, that one I don't think I need that. Substituents that are 3 carbons in length have higher mu receptor affinity as an antagonist than those with 4 carbons. So what does this say? Substituents that are 3 carbon in length have higher mu receptor affinity as antagonists than those with 4 carbon atoms. Optimal antagonist potency is obtained when the N substituent chain is 3 carbons in length. All we are saying 3 to 5, but all they are just saying here, further emphasizing, is like when you have the allele. The allele, I think we say the allele is the one which gives us the naltrexone. No, sorry, the naloxone, sorry. Allele gives us the naloxone, and allele is 1, 2, 3. All we are saying is that when you have 3 carbon atoms, you are saying 3 to 5 for antagonist activity. So we are saying 3 carbon atoms is responsible for maximum antagonist activity compared to 1, 2, 3, 4, or 5. Like you can also have methyl butyl group. You can also have methyl butyl group, like you have compounds which have CH2 and the butyl group there. And all we are saying is that those groups, they will have antagonistic activity, but maximum antagonistic activity is obtained when the nitrogen at position number 3 substituted with 3 carbon atoms. And since we have said also unsaturation increases antagonist activity, again, the allyl group has maximum activity. So this is just further highlighting of what we have discussed about that group. So optimal antagonistic potency is obtained when the end substituent chain is 3 carbons in length. It includes allyl and methyl isopropyl. Methyl isopropyl has 4. Allyl has 3. Methyl isopropyl has 4. So of course, allyl will have more an antagonistic activity than when we have 4 here. Example, naloxone. So we have naloxone, we have even naltrexone, we have also naloxone. At 5 carbons, antagonism is lost and agonist returns due to interaction with site A. Removal of carbon 15 breaking ring D decreases mu receptor affinity. That again, we will look at that later. So, but we will find that there is no time. Ring D must always be intact. The ring D is a piperidine ring. We can never break that ring. That ring must always remain intact for activity. But all we are saying, I hope that this is just putting it very clearly, that we are saying between 3 and 5 carbon atoms, we attract antagonist activity. Maximum antagonist activity being given by the 3 carbon atoms found in naloxone, whereby you have an allyl group. And of course, as you increase the carbon atoms, the attraction will slightly decrease, but you still have good antagonist activity. No wonder you have also naltrexone, which is also a pure antagonist. Other drugs like naloxone are actually partial agonist. And so this is just further showing us that position number 17, or the nitrogen at position number 19, the substitution at that position is very, very important. And we can't be able to account for the change in activity. We have said if we put a very big group, it will also interact with site A, and in interaction with site A through hydrophobic interaction, those are the dipole and so on, through hydrophobic interaction, that gives better agonist activity. When you increase the size of this substituent at position number 17, you can also have an influence on the binding, that as you increase between 3 and 5, you decrease the binding of that group to the receptor, and therefore you encourage antagonistic activity. So we can't be able to explain that activity. And now we are looking at here, we have summarizing the effects of watering chain length on nitrogen of morphine structure. So now you're looking at morphine. So the only group we are interested in is that group there. So you can have R as a methyl group, and of course that is morphine. You can increase it to an ethyl group. You can increase it to a propyl group, and as you continue increasing the group, we are saying agonist activity decreases, antagonist activity starts to increase. If you do 1, 2, 3, 1, these are 1, 2, 3, 4. This is for the alkyl group. If you do it just an alkyl group of 4, then you do not have any activity. So we are only saying, therefore, that group is very, very important. Then again, we can have again at the same position. We said when now you increase beyond 5, you can see these are 5 carbon atoms. So beyond 5, so these are 6, and then you can see that this is the maximum now, which I've been talking about, the ethyl phenyl group. This has very high analgesic activity, and this is because, as we have said again, of interaction with the A site. So I think that, of course, as you have seen, I don't think you can also go beyond CH2 5, CH3, because again, remember, there must always be a balance between the lipid solubility and the water solubility. When you make the molecule again too much lipid soluble, there will be depolarization. To undergo depolarization within the periphery, and therefore it will remain in the lipid membranes or in the lipid in the lipid layers, and it will not be able to be available to penetrate. It will not be available to penetrate the BBB. So all we are saying is that interestingly, unlike most of the other compounds or drugs we have looked at, there is increase or change of the substituents in terms of increase of R does not have the same effect. It depends on the size and the structure of that group, because we have seen when you strain it, like when you make it a cyclopropyl. Remember, when you strain and give a cyclopropyl, the strain kind of constricts or constrains that molecule. And although the molecule has 3 carbon atoms, it can behave like it has 2 carbon atoms. And even the same case would apply when you increase that group. So when you bring in strain, when you bring in unsaturation, when you slightly increase that group, then, as we have already noticed, then you can change the activity of that compound. I think we can end there today, unless if we have any questions. Any questions? Because this now that the base will be having a change, we'll be adding another ring. So I want to do that next time. And you have done many slides. You have done 52 slides. Oh, that's good. But I hope you have understood. Is there any question? I hope you can be able to factor difference, and we are looking at change from morphine to oxymorphone. The first thing you'd have to do, if you have not been given the structure, is you must be able to draw your morphine structure, because you want to show that you know the change that was occurred. You start with your morphine and you're going to oxymorphone. So you want to be able to draw that structure from morphine to oxymorphone, and you draw the structure and you show the groups that have been changed, and now you just discuss those groups. You don't bother with any other group, because we are looking at the influence in analgesic activity on change of morphine to oxymorphone. So you don't now start bothering. The N-methyl group still remains the N-methyl group. The methoxy group at position 3 remains the same. So you don't now start saying, the methoxy group is needed for activity. The N-methyl group, those are remaining the same. Morphine has a 3-methyl group, 3-hydroxyl group. Oxymorphone has the 3-hydroxyl group. Both have the N-methyl group. This other one has the N-methyl group. They have all the rings. Even all the rings are the same. So you don't now start telling me, because some of you go to so many things. You find somebody who start even telling you remove all of the furan ring. You ask yourself, where has the furan ring been interfered with? So the important thing, especially when you're looking at a structure modification from one structure to the other, can you be able to draw the starting structure, then number it correctly, and then draw the final structure, and again number it correctly. And then from the original structure, the starting structure, and the final structure, ask yourself which constituents or which substituents have been changed, and discuss the substituents that have been changed. And once you discuss the substituents which have been changed, because I'm not asking you for the SAR of morphine, so you don't need to tell me the pentacyclic. You don't, because I'm only saying how has the structural changes from morphine to, let's say, oxycodone or whatever structure is, or morphinan, how have the structural changes influenced the analgesic activity? So don't bother with the SAR. Don't tell me the match, just look for the structural differences and only talk of the structural differences. Because what I find is that most of us want to talk so much, even the irrelevant. The irrelevant is correct, yes. The statements you give me as correct, but they do not differ, or they have no association with the question. So therefore, you have wasted your time. So I hope even we can be able, from what we have done today, we can be able to discuss the metabolism. We can be able to discuss how the peripheral changes, how the change in the peripheral groups within morphine alter the analgesic activity. And in some of the cases, as we move on, we are even being able to explain why do they alter the activity. The only, before I close now, because that was at the end, I think I could still show you, because I've mentioned it severally, though it is at the end. Yeah, I would want you to see. It is at the end somewhere. Yeah. Here we are. This is what we are talking about. That we have the different, this is our site, this is our receptor here. So this here is our receptor. This is our opioid receptor there. And this opioid receptor is the one we are saying you do have your aromatic ring, and you can see it will interact with the D receptor. We interact the D receptor through lipophilic interaction. Of course, we do have our 3-hydroxyl group, which will also further anchor this molecule into the receptor. That one is not shown, but the hydroxyl group, we have said, it will also further anchor this molecule onto the receptor through hydrogen bonds. Then from there, you have the C receptor. And this C receptor, you can see, you have further groups here, this portion here, these further rings, this ring, and even that ring. Further, so this ring, especially this ring here, further interacting with that receptor also through hydrophobic bonds. And then you have the tertiary amine, which the tertiary amine interacts with the B receptor through anionic bonds, because we are saying this is a tertiary amine. It can be protonated at physiological pH to give us a cation. And within the receptor, we will have an ionic site. So the cationic site and the anionic site will interact through ionic bonds. Again, very, very important. So you can see this molecule. So it has the hydrophobic areas. The hydrophobic areas will interact through hydrophobic bonds, and the anionic site, which is the terminal nitrogen, will interact through anionic bonds. Then, as I said, you can see the group we were talking about. This group is even found. So this is one of the groups that you can find. You can find it either at position number 17, or this large group. You can find it in other positions. Like when we look at the buprenorphine, you will find that this group is not at position number 17, but that group that is provided, or if it is provided at position number 17, can be provided at position number 17 or at another position of this molecule. You can see the A receptor, which we have said, and it will offer additional, the aromatic group of that group will offer further hydrophobic interaction, either through dipole, induced dipole interaction with an A site. So when you look at morphine, morphine is up to there. So morphine does not interact with that receptor. So when you have that big group, either at position number 17 or in another appropriate position, it allows for further interaction. When you have a molecule interacting closely, binding strongly with the receptor, then you expect that there will be good activity. So that explains the interaction of the opioids with the receptors at different positions of the receptor. This we have already mentioned is just a conclusion or a summary, but I think we do that when we finish. So I have just remembered it would be good for you to, you can also look at for that receptor, you can be able to get it. Even if you look at your reference books, you can be able to read how morphine interacts with the receptor. I think with that, unless if we need to sign in kawaida, but unless if we have any question, then we can close there. And I think we have done well. It is my hope that we will finish narcotic analgesics. There are about 102 slides. We have already done 50. So I think we should, if we move fast, we can be able to do the rest 50 next time, because the unit has quite a number of subtopics which we need to take care of. So I hope you are okay. You don't